Boldly going where no science show has gone before. The Naked Scientists.
On The Naked Scientists this week, how sharks really sniff out a snack, the genes that stop you from snacking in your sleep, and the World Cup in South Africa, how technology is making the game safe and accessible to all. I'm Ben Valsler, and with me today is Kat Arney.
Hello. Today we're celebrating 50 years of lasers. We'll be discovering the history of the laser, as well as exploring the future for laser science, including how lasers could provide all the clean energy we need. Plus, Mira explores the role of lasers in high-precision measurements.
Thank you very much, Kat. Also, I have been to the University of Bristol to find out how lasers can actually be used as tweezers to move around objects that are less than a third the size of a red blood cell. And Dave has built his own laser in his garage. Find out more in Kitchen Science later on.
I cannot wait to hear that. And in our question of the week, Diana will be looking at light to find out what happens if you're driving at the speed of light and then switch on your headlights.
If you would like to contact us through Twitter, it's at Naked Scientists, or you can send an email to chris@thenakedscientists.com.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
This is The Naked Scientists with Kat Arney and Ben Valsler. Now, Ben, what have you got for us in the news this week?
Well, sharks are well known for their ability to follow a scent in the water all the way to their next meal. And now researchers in Florida have discovered how it is that they do it. Writing in the journal Current Biology, Jane Gardner at the University of South Florida and Jel Atima at the Woods Hole Oceanographic Institute showed that sharks are able to detect very small delays in the scent reaching each nostril, and it's this, rather than the actual concentration of the chemical, that actually gives them their sense of direction. Now, most species that rely on scent are equipped with stereosensors, so 2 antennae on an insect or 2 nostrils on your dog, for example, and it's long been assumed that this means species can home in on the source of a scent using concentration as a guide. So if the scent is stronger on the left than on the right, they would simply turn into the concentration gradient.
Well, that sounds fairly sensible.
It does, you'd think it makes sense, but in reality, concentration gradients are rarely, if ever, that simple. When dispersed in air or in water, chemicals are very unlikely to form a uniform gradient. Instead, they exist in whirls or vortices, and sometimes you get peaks of concentration quite a long way from the source. Now, this means that following a concentration gradient alone is quite likely to lead you in circles, which is not a very efficient way to find your food.
And as we know, sharks are devastatingly efficient hunters. So what have the researchers done to find this out?
Well, working with the smooth dog shark, that's Mustulus canis, the researchers introduced a scent to each nostril in very controlled concentrations and with very controlled time delays. They found that the timing of the pulses was most important, as the sharks would turn towards the first pulse, even if the second pulse was actually a much higher concentration. This actually seemed to break down when the delay was too large, so if it was over a second between reaching one nostril and then reaching the next, the shark was just as likely to turn either way. Now, what this means in practice is that the sharks will actually weave from one side to the other, following the average concentration gradient, without really being waylaid by the local small concentration changes.
Well, that's dog sharks, but what about other types of sharks? Great whites, the scary ones with teeth.
Well, the researchers want to follow this up, and dog sharks are actually quite cute. But they want to follow it up and see if things like a wider spaced nostril gives a shark greater accuracy and at higher speeds. The best example to think of is hammerhead sharks. Now, they have these distinctive flattened heads that we call cephalofoils, and they have much greater separation between their nostrils. And even though their olfactory organs are just as sensitive as other sharks, they might be better able to detect these time differences, and so they might be able to hunt more efficiently at sharper angles and also at higher speeds. And the really nice thing about this finding is it has some other very interesting applications. It can be applied to underwater steering algorithms to allow unmanned robotic craft to very quickly locate the source of a chemical spill underwater, such as, for example, an oil leak, which of course is very important at the moment.
Very topical. I do not want to be the scientist that has to do research on hammerhead sharks. Anyway, now we have a dilemma for you, Ben, the classic Homer Simpson dilemma. Is it more important to eat or to sleep? Now, if mammals are deprived of sleep, then they want to eat more to help them stay awake. And if you're deprived of food through starvation, this keeps you awake, presumably to search for more food. But we don't know a lot about how this is controlled, and obviously we need to strike the balance between enough sleep and enough food. Though you can combine them. Obviously, I once had a dream I was eating a giant marshmallow, and when I woke up, my pillow had gone.
Ba-boom.
Anyway, now researchers in the US have uncovered some of the genes that control the balance between eating and sleeping, at least in fruit flies, and in turn this might shed light on our own patterns of eating and sleeping.
OK, so what's the story here? What are they looking at?
Well, this is work from Alex Keane and his colleagues, and they published it this week in the journal Current Biology, and they've been looking at the sleeping and feeding cycles of these tiny fruit flies, Drosophila. Now, these are quite a handy model organism for this kind of study because we know a lot about their daily rhythms, these circadian rhythms. Now, the scientists discovered that starving fruit flies had a powerful effect on keeping them awake, the same as you'd see in mammals. And given that fruit flies share a lot of genes with humans and other mammals, this suggests that we can use them to unpick the genetic connections between sleeping and feeding using these little flies.
OK, there are lots of genetic techniques that people can use to study these sorts of things. What did this particular research use?
Well, the scientists scanned through 2,000 genes in the flies, and they found over a dozen of suspects that were involved in sleeping and feeding, and they narrowed their search down to just two that seemed to be really important. These are genes called clock and cycle, and we've heard of them before because they're also involved in flies' daily rhythms, and they're involved in the daily rhythms in mammals, including humans. Now, to find out more about the role of these genes, they looked at flies both with and without each gene under starvation conditions to find out how much they slept.
I don't think I've ever seen a fly that I could definitely say was asleep. How on earth do you tell?
Well, the researchers monitored the fly's movements. Now, if a fly isn't moving regularly, it's probably a good bet that it's asleep. Anyway.
OK, so what did they find? They've monitored their sleeping flies and their waking flies. What did they actually find?
Well, the researchers discovered that flies missing the clock and the cycle genes had a 3- to 4-fold reduction in sleep when they were starved, compared with genetically normal flies. And this tells us that both the genes play an important role in helping the flies to sleep under starvation conditions and probably help to coordinate the choice between sleeping and eating at any given time.
OK, and we know the clock and cycle genes are also shared between us and the flies, so this is all well and good if you're a hungry or sleepy fruit fly. Still never seen a fly asleep. But could this research have any relevance to us? We're a very different species.
Well, we do have these clock and cycle genes, and they do have very similar roles. And it may be that these genes do help us to coordinate our eating and sleeping patterns too. So further research with mammalian models and human cells, it might shed light on how to treat things like sleep disorders and metabolic and eating problems. But it's quite speculative at the moment, and more work does need to be done.
Well, as always, if anybody is doing research on sleep and would like to pay me to fall asleep, they are more than welcome. I do like a nice nap. Thank you very much, Kat. Now, collecting mosquito saliva in honey can help to track the pathogens that mosquitoes carry, according to researchers in Australia. Andrew van den Hurk at the University of Queensland and his colleagues have published a report in the journal PNAS detailing how mosquitoes can be coaxed into leaving saliva samples in honey-soaked cards. These cards can then be analysed to find any virus RNA present, giving you a precise guide to what viruses local mosquitoes are carrying without ever having to handle a mosquito.
Mosquito spit, lovely. Why would we be looking for pathogens in mosquito spit?
Well, arthropod-borne viruses, or arboviruses for short, are a public health concern worldwide. They include things like dengue, yellow fever, West Nile virus, Japanese encephalitis, lots of really quite troublesome viruses. Proper surveillance of these viruses is essential for disease control strategies such as timing vaccination correctly and mosquito control. But present mosquito-based survey techniques are, according to the paper, expensive and logistically problematic, which I think is a tactful way of putting it, and they involve the collection and transport of live mosquitoes. Other survey methods might involve disease diagnosis in infected patients. You have to wait until you have enough infected people to understand it, or monitoring of sentinel animals to see what diseases they're carrying. Again,
another scientific job I would not like, studying live mosquitoes. So what is so good about this technique then?
Well, the honey trap method has several advantages. The honey soak cards themselves preserve viral RNA for at least 7 days without needing to be refrigerated. And this is even when tested in both temperate conditions, which was at a site near Bunbury in Western Australia, and in much warmer, damper tropical conditions near the northern Queensland city of Cairns. The honey itself is also a very important part of the process, as it remains moist throughout the collection period, and that ensures that the mosquitoes have access to the liquid sugars that they find so attractive. Manuka honey, which is partly what they've been using, also has antibacterial properties which help to protect the viral RNA from bacterial RNases, these enzymes that break down RNA, and this preserves the sample for long enough to be collected days later and analysed.
But how do they know this technique's actually working? Is it good? Does it work?
Well, it seems so, yes. In lab tests, by adding blue dye to the honey, the researchers could identify which mosquitoes had been feeding on the honey and then compare evidence of virus on the card to the traditional saliva samples taken from the mosquitoes. This showed the method to be of similar or better accuracy to the traditional, more time-consuming sampling methods. In fact, there were some virus particles that were transmitted even without the mosquitoes consuming any honey, and this is because an infected mosquito just probing at a food source is actually enough to transmit a virus to a susceptible host. Now, this particular report shows that this novel technique works well for Ross River virus, Barmah forest virus, chikungunya and West Nile virus, but the authors suggest that it could be expanded to detect malaria or even used with other virus vector species, so it's very, very promising.
The wonders of mosquito spit. Anyway, moving on. Cancer is a disease that starts when cells become immortal and multiply out of control. And over the years, researchers have discovered that a crucial part in the process, for at least 8 out of 10 cancers, is the switching on of telomerase. This is a protein that makes telomeres, the caps on the ends of our chromosomes. They're a bit like the plastic caps on the end of your shoelaces. Now, without telomerase, our telomeres get shorter and shorter, and eventually, when they get too short, the cell stops dividing. It's a bit like a molecular clock counting down the lifetime of our cells. But cancer cells switch telomerase back on, so they just keep on multiplying. And now new research from scientists in Cardiff, funded by the charities Cancer Research UK and Leukemia and Lymphoma Research, have discovered that a certain type of leukemia may actually develop as a result of telomerase not being active enough.
So hold on, the usual problem is telomerase is too active. The problem here now is it's not active enough. I'm confused. What's actually going on here?
Well, led by Duncan Baird, the scientists were studying samples from patients with chronic lymphocytic leukemia, or CLL. This is a cancer that affects white blood cells, which multiply out of control. And writing in the journal Blood, the scientists used a new technique to precisely measure the lengths of telomeres in the cancer cells and compared them to telomere lengths in blood cells from people without the disease. And they found that telomerase appears to be underactive in the cancer cells in the early stages of the disease. So the telomeres actually get shorter and shorter. Now, at this point, you would expect the cells to stop dividing and to die, but they don't.
So what's actually happening? What's going on?
Well, instead, the ends of the chromosomes start to stick together. This causes strange genetic alterations that further fuel the development of cancer. And then the researchers think that telomerase actually gets switched back on at this point, immortalising these genetically weird cells and fueling the growth of cancer.
So this is a two-step process. At first, a lack of telomerase leads to some genetic faults, and then the telomerase is switched back on, and these faulty cells, these mutants, then grow out of control.
Exactly. And this is the first time that this process has been shown to happen in human cancer cells, so it's pretty important stuff. And what's more, the research could potentially lead to a blood test for monitoring how fast leukemia is progressing by measuring telomere length, as well as helping doctors to decide on the best treatment or speeding up diagnosis.
Now, this sounds really good. Anything that quickens diagnosis is a benefit to us. But do we think the same sort of thing is happening in any other cancers other than leukemia?
Well, that's what the scientists are trying to find out now. They're looking at telomere length in other types of tumours, such as bowel cancer. And at the moment, we don't have the results from this work. But if they find similar mechanisms at work, it could open up some really exciting new avenues of research. And that could lead to future cancer treatments or diagnostic techniques.
Fantastic, that's very good news. Now, it's World Cup season again, so everywhere you look, there's football. I'm sure you've been following it, Kat.
Yeah, I was wondering, was there some kind of sporting thing on? I hadn't really noticed.
Well, it's probably worth keeping an eye out for, but to be honest, you'll find it very hard to avoid. But there's actually some very interesting science going on behind the widening access to football in South Africa, as Mira Senthilingam found out.
This week saw a historic moment in football, the kick-off of the first World Cup ever to be held in an African nation. I spoke to Kelvin Kem from Pretoria in South Africa to find out what things are like over there and how science and technology is being used to make sure the games are as safe and accessible to as many people as possible in South Africa.
Well, Mira, everybody's going World Cup mad here. On the large TV masts and the cell phone masts, there's huge soccer balls on the mast. Everybody's got soccer balls all over the place. On every placard you can imagine, there's soccer pictures. All the teams are arriving day by day, and every team is being met at the airport and waved down the street. So just everybody's riding around with flags out of the car windows, and so you can't look anywhere now that there isn't soccer fever all over the place.
And have there been any particular science or technological developments in relation to the World Cup, say to help people watch it or even for security reasons too?
Oh, there's been some interesting things. For example, one company has taken a number of solar-powered television sets into far remote areas that are not electrified, so all the local villagers can come along and sit and watch the World Cup on TV. Also, something else is interesting about the security, as you mentioned. There's huge security coverage. For example, if a model aeroplane takes off, a radio-controlled plane, and aims towards the stadium, the Military and Security Command Center can detect that model aeroplane and crash it if it goes on a path towards a soccer stadium. By radio jamming, they will jam the radio signal so the aircraft crashes. And even base jumpers, every base jumper has got to be registered and can't jump within a certain radius of the stadium unless they get permission, which they won't get during a game. But large and small aircraft as well, every single aircraft from a small private aeroplane to the Boeing 747s has got to ask permission to cross a 100-kilometer radius around the game every single time they cross. And we're talking about thousands of occasions. And each one has to be individually certified, and the planes have all had to register beforehand so they know exactly who owns the aircraft and what it's doing. So any strange aircraft will be stopped. Something else, too, which the world can look forward to is that the massive television coverage there's going to be. Each stadium has got something like 32 cameras per game, operated through a giant television coverage center that has been specifically put aside for the soccer only. So it'll run 24 hours a day, just sending TV all over the world. It'll be the largest international television traffic that's ever been sent out of South Africa as the coverage of the soccer.
That was Kelvin Kem in Pretoria, South Africa, talking to Mira Senthilingam.
Now, as well as blanket football coverage, it's been very hard to miss news about the oil leak in the Gulf of Mexico. Estimates vary widely, but it's thought that millions of gallons of oil have leaked into the ocean. But what impact will this have on the local environment? Well, Dr. Robinson Fulwiler is a researcher at Boston University, where she studies the wetland ecosystems such as those in Louisiana that are likely to bear the brunt of the oil damage. Robinson, thank you so much for joining us. First of all, what are the environments that you're looking at, and what do they normally look like?
Sure. So we're particularly interested in the wetland environments. So these are sort of the grassy, vegetated areas, and they have lots of different types of vegetation, both wetland grasses, but mangroves as well. So they're very dynamic systems. And normally, we expect them this time of year to be growing a lot. There's lots of new shoots, so lots of bright green coming out. And then, of course, these environments are filled with lots of different animals, so a variety of birds and fish and snails, all different things.
So quite a biodiverse area, actually.
Absolutely.
How do you go in there and assess an ecological impact of an event like an oil spill?
That's a really good question, and I think it's going to be a challenging one to answer. So the first is that Louisiana's wetland ecosystems have really been studied for a long period of time. So we've got a lot of kind of historical data, before the oil spill. And now we're all about going in and trying to find areas that have been impacted and starting to measure certain things to see, how has it changed from after the oil spill. So we collect samples and then bring them back to the lab for analysis.
And what sort of damage have we actually seen so far?
It's tough to say. So in some cases, it's really obvious. When you pull the boat up on shore, you can see that the wetland grasses, their shoots are covered in the oil. Just to give you an idea of what that oil is like, it's kind of like when you make a sundae, it's got that caramel, melted caramel and hot chocolate. It's got that kind of texture to it, so it's really thick and gooey and sticky.
You're making it sound very appealing, whereas I'd imagine oil
not delicious.
Isn't so nice.
You don't want to eat it. But that's the only way I can describe how sticky it is. So it's covering a lot of the shoots of the grasses. You can see it on some of the animals themselves. Of course, you've seen those pictures of many of the birds and stuff, but when you go into the wetland, you can see it even on crabs and snails and all over the plants. We even saw some dolphins that had it on their fin and that kind of thing. So at this point, we know that it's definitely coating the organisms, and it's also coating the sediment layer. And I'm very interested in some of the organisms you can't see, the microbial community, and we know now that oil is simply making sort of a lid over all of the sediment and the grasses, and that's what we're trying to figure out how that will impact the system.
So what do we think can be done to remedy the damage that we've seen?
That's another really tough question. So there's actually been this great YouTube video that Irv Mendelson made, and he's from Louisiana State University, so people could Google it. But he sits down and goes over all of the different ways we could try to remedy this situation, and there's probably three most common ways. One is you can, and you've probably seen this on the news too, you can burn the oil off, and they've been doing this in the open water. You could do that on a wetland too, as long as there was a layer of water. So you'd burn the growing vegetation now, but you'd also get the oil off the land, and if the oil hasn't seeped into the sediment, the roots should be able to regenerate and grow again. So you could do that. Another thing is to add nutrients, and if you could add things like nitrogen and phosphorus, you can stimulate the biological activity of the wetland and help the microbial community break down the oil. And then probably the third way is just to sort of let it take its course, and over time, the thought is that over time the oil would start to degrade and go away.
Okay, so none of them are an immediate fix, of course. But why are these environments so important to us? We've discussed the fact that there's a great deal of biodiversity, but wetlands are also very important for the local people living there, but also on a countrywide scale, wetlands are vitally important.
Sure. I mean, this is really a major cultural and natural and economical piece of land here for the United States, and I think really for the world as a whole. The wetlands are important for a lot of fish species that we like to eat, right? So commercial species that are good, and then of course they're important for birds and lots of nursery habitats, but they're also important for things that we tend not to think too much about, like the filtering of nutrients. So they can act as a filter to remove things like nitrogen and phosphorus that humans put into the environment. And so that's kind of an ecosystem service that is maybe goes overlooked and is really important. And we imagine that putting the oil on these wetlands will change how they filter nutrients.
So it could have slightly longer term and more economic impacts than we actually thought. Robinson, thank you ever so much for joining us. That was Dr. Robinson Fulwiler from Boston University. She's been down to Louisiana to assess the ecological impact of the Gulf of Mexico oil spill. If you'd like to hear any more about any of her news stories or read about them, you can find them online at thenakedscientists.com/news.
Bringing the facts to bear. The Naked Scientists.
Now, this week, we are celebrating 50 years of the laser. And to fill us in on the background of the laser and some of the cutting-edge applications and research that's currently going on, we're joined by Dr. Graham Hurst, and he's the head of laser application at the STFC's Central Laser Facility. Hi, Graham.
Hello there, Kat.
Hello. Let's start off by asking the question, what is a laser? What is a laser and how does it work?
Well, I think most of us, we have an idea of what one of these things looks like. It's a small box out of which comes a very bright beam of light. And I guess what you want to know is what's inside. The word laser stands for light amplification by stimulated emission of radiation. So what's inside there is an amplifier. It's a device where you put a little bit of light in and you get a lot more light out. And usually that comes in three parts. So there'll be some stuff which does the amplifying, some material. There'll be a source of power to pump that stuff to keep it in an excited state where it's capable of amplifying. And then there will usually be an arrangement of mirrors. And what the mirrors do is take control of the beam. So instead of the light coming out in all directions in an uncontrolled way, you get that nice pencil-like beam out of the end.
So you've got a very intense beam of light that's can really be controlled in a very precise way. What sort of frequencies of light can we use? We've had a question in from Kelvinator on Twitter who says, can a laser light be from anywhere in the spectrum of light?
These days it can, yeah. I mean, the very first laser that was produced worked in the near infrared. It was really, really bright, so you could probably see it, but only just about. And gradually, as time went on, more and more lasers were developed with a wider range of available colours, a wider range of available wavelengths. And these days, the range is spectacular. Just last year, a group of scientists in America demonstrated a really high-power laser that's actually working in the X-ray region.
That's pretty powerful, I should imagine.
Very scary thing, yeah.
Lasers have been around for about 50 years. What was the background to lasers? I've heard them described as a technology looking for an application. How were they first invented?
Yeah, solution looking for a problem. They grew from background research on microwave amplifiers, which, if you like, is a sort of very short wavelength radio wave. And as the wavelength got shorter and shorter, and light, if you like, is just a different kind of electromagnetic radiation, there was a race on to be the first one that you could see, essentially. And Ted Mayman generated this Ruby laser back in 1960, 50 years ago, first laser you could see, and he won the prize. Since then, the applications have just spread out enormously. To begin with, they were a very useful research tool. But pretty quickly, people got the hang of the fact that you could cut and weld with these. And you'll remember the James Bond film, Goldfinger, where cutting and welding is very much to the fore.
Absolutely. We do seem to see so many applications, from laser light shows at pop concerts. If you follow fashion, laser cut shoes are very in at the moment. You can have laser surgery on your eyes and presumably a whole host of very technical applications. What's the sort of diversity that lasers are used for nowadays?
Oh, just about everything. I mean, you look around your house, you'd be surprised how many things have been made by a laser. Pretty well all the silicon chips, your flat panel TVs, as you say, a lot of stuff's been cut. We're working on quite a range of applications here. Everything from using lasers to look inside blister packs that have tablets in, just to make sure that the tablet really is what it says on the outside of the box, all the way through to trying, as you mentioned in the intro, to sort out the world's energy crisis. What are we going to do when we can't use fossil fuels anymore?
So how can we use lasers to make energy?
Well, if you think about fossil fuels, what they are is they're essentially stored sunshine. Almost all the energy that we use on the Earth now started out of sunshine. And the natural process that drives sunshine is called fusion. And the idea is to use high-power lasers to get that fusion process under control here on the surface of the Earth. And then you can take isotopes of hydrogen, you can glue them together in the fusion process, you make helium, and you release energy. And that's the way the sun works, and that's the way we would like to do it.
And we've had a question in here from Paul Anderson, who's in New Zealand, who says, say if you're using solar arrays in the desert, it would take enormous cables, very expensive cables, to transmit the electricity. But could we convert the energy into a laser beam? You could bounce it off a satellite back to Europe. You wouldn't need cables at all. Could we transmit electricity by laser light?
It is an interesting thought, yeah, and in principle you can. People have looked at it for a number of applications. One is, can you use it to power that satellite? Satellite power is a tough challenge. And yes, in principle it can be made to work, but there are issues, obviously. You'd have to decide how you're going to keep people you wanted out of the way of the beam. It's kind of unwritten rule that you never point a laser at anything you don't intend to. And so you would have to ask how you made sure it didn't go wrong. You've also got efficiency issues, because even now, even with the very best lasers, they're not 100% efficient at getting electricity into light and then converting it back again.
Well, yeah, we've in the question if you wouldn't want things in the way, we've had a question in from David Wally, 94 on Twitter. It says, if you shone two lasers directly into each other, what would happen?
Well, that's a good question. If you shone them directly into one another, you're quite likely to break the lasers, unfortunately. But if you imagine you misalign them slightly so that the beams cross, but that they don't go down the throat of the opposing laser, then if you were to do that in a vacuum, if you just have one light beam crossing another, then to all intents and purposes, nothing happens. Once you get to extreme physics conditions where the laser intensity does become spectacular, and in some experiments we do, we're getting there, you might imagine that you can perturb the vacuum. You can change the vacuum with the intensity of light you need. But mostly this is interesting if you cross the two beams over in some kind of material. And if you do that, you can achieve all sorts of interesting effects in the material by combining two laser beams through the properties of the material.
I love the idea of extreme physics. Just to return to the sort of applications of lasers. So we can do all these things. We can use them for seeing stuff. We can use them for cutting things. What actually determines the properties of an individual laser? How can you change them, tweak them?
Well, if, for instance, you wanted to change the colour of the laser beam, then you would either have to change the stuff that's doing the stimulated emission. And in the past, we've used everything from liquid dyes to solid crystals to gases. You can get a whole range of different colours that way. If you want to change the properties of the beam itself, if you want to focus it down or blow it up or propagate it a long distance, then you would change the mirrors. You would alter the optics, or you would put other mirrors in.
So basically, there's just pretty much anything you can do with lasers. Is there anything lasers can't do? That we'd like them to do.
There are quite a few. I mean, we're still working not only on finding new applications for lasers, but there's still a lot of work on the better laser, if you like. And as I say, it was dramatic results recently in the States, pushing the laser wavelength down into the very short part of the spectrum.
What could you do with an X-ray laser?
Oh, what can you do? Well, you can do all the things that you can do with an X-ray light source, only 1 million or 10 million or 100 million times more quickly or faster. So, for instance, they were using them for attempting X-ray imaging. They were trying to probe X-ray signatures of elements. There's a whole range of science that would have taken weeks that can now be done in seconds.
Wow, it's some extreme physics. Anyway, thanks, Graham. Graham's going to stay on the line with us. That's Graham Hurst from the STFC's Central Laser Facility. And so if you have any laser questions for Graham, if you want to contact us through Twitter, we had a lot of questions in from Twitter tonight, it's @NakedScientists, or you can send an email to chris@thenakedscientist.com.
Now, the field of metrology, or measurement to you or I, is something that requires a great deal of accuracy. And this week, Mira Senthilingam has been out to find out more about this science and the crucial role that lasers play.
This week, I've come along to the National Physical Laboratory in Teddington in Middlesex, which specialises in the science of measurement, that's metrology. And what's interesting is that lasers play a crucial part in the science taking place here. So here to tell me more about that is Jonathan Williams, leader of the Quantum and Electromagnetic Division.
So NPL covers a wide range of measurement for all the physical sciences. What we do is develop specialised techniques to serve a wide range of applications, as you mentioned, all the way through precision manufacturing, through the measurement of time, through measurements for healthcare, so that people get the right treatment when they go in for radiotherapy in hospitals, for example.
And how are lasers used here then, and how crucial are they to this wide range of science taking place?
The principal things for us with a laser are as it's highly collimated, so it travels in very straight lines, and it also can be constructed to have a very stable frequency or wavelength, and these are two key aspects that allow us to use it in metrology. The travelling in straight lines is important because it means you can use it to measure distance. You can also use it to do measurements at a distance. So, for example, you can use it to scan the atmosphere and measure the amount of pollutants, say, above an oil refinery. So this is a principle like radar, where, of course, radar measures things like aeroplanes using microwaves. The equivalent technique with a laser is called LiDAR, and it has two advantages. It can pinpoint where emissions are coming, say, in the form of hydrocarbons or sulfur dioxide, and it can tell you how much material is there and also exactly where it is in terms of distance and angle. We designed a specific laser van, we call it, or a LiDAR instrument at NPL, and this van drives around the world, in fact, and it can then scan right across an oil refinery from within one place. And it has a very complicated suite of lasers inside that are tuned to the exact atmospheric pollutants that you're looking for.
Now, when describing these things, I'm imagining a constant laser beam being used in order to make all of these measurements. But you can also work with lasers in pulses as well.
That's correct. I mean, a lot of people think of a laser as a continuously operating device. It shines all the time. But you can set them up to make very, very short pulses, where short is 1 millionth of a second, the picosecond timescale. And this has a wide range of application in measurement too. In particular, we use these very short pulses to make short electrical pulses, very tiny impulses of electricity, and then these are used to characterise very fast electronics.
And what applications does this pulse format of lasers have?
Well, the biggest application which we all benefit from these days is in communications. A lot of communication now is done over optical fibre, some even into the home, and these systems rely on very short laser pulses to carry the information in a very sophisticated form of Morse code. So what we do in metrology is we have to understand how well these lasers work and what their equivalent bandwidth is and their reliability.
So that's a wide range of applications of the laser here and, well, generally in science. But where can you see, then, the use of lasers being taken next?
So the future sort of science horizon is to use laser light at very low intensity levels, so small, in fact, it breaks up into its smallest components, what we call photons. And the possibility there is you can then send single photons as pieces of information, And you can do communication in a very secure way where you send your message as a series of 1 or 0 photons. And this has great attraction because in theory it's an unbreakable system.
When it comes to measurements, a key application of the laser is in length measurement. And with me now to explain more about this is Ben Hughes, who's the Principal Research Scientist in the Dimensional Measurements Group. Ben, something that most of us are probably familiar with is we'll see the surveyor at the side of the road holding some kind of handheld laser device, or the estate agents wandering around properties measuring the sizes of rooms. So how do these actually work, and what are they actually measuring by the use of lasers?
The handheld device that you've mentioned that an estate agent may be using is based on a time of flight measurement. And it's based on the principle that distance equals speed times time. Now, we know the speed of light very accurately, so all we have to do is measure the time it takes for a pulse of light to travel from the device to the wall at the other end of the room and back again. Now, given that the speed of light is very high, 300 million metres per second, it means that, say, a round trip to, say, a wall that's a metre away will take something like 6 nanoseconds. You need some very fast electronics to be able to time that very short time. You have a measurement resolution of something like 50 millimetres. So that's the kind of precision that these devices are operating at.
Now, that's just one application, though, of measuring length. We are here in the Length Lab at NPL, and here you measure things on a much larger scale with a device that we've got here just in front of us, which is a laser tracker, which can measure things as large as aeroplanes.
This laser tracker is sending out a thin pencil beam of laser light. Now, you can think of that laser light as being a ruler. Now, on a conventional ruler, the graduations would be perhaps in millimetre spacing. On this ruler, the graduations are spaced by exactly half the wavelength of the light. Now, on our particular laser, the wavelength is 633 nanometres. That is 0.000633 millimetres. So that means every graduation is half of that, which is 315, 316 nanometres. Now, what we can do with our laser tracker is we can use the laser beam to track a reflecting ball as we move it over our object, and the laser tracker is counting those graduations on the laser beam. So it's getting a very high accuracy measurement of where we're moving our ball.
And now you have this tracking ball, essentially, which is a reflective ball here in front of us, and it's only about 1.5 inches in diameter. The actual device where the laser is generated stays still on a desk. The laser hits this ball and then stays, basically, on this ball. So as the ball moves around, it keeps attracting the laser to it.
Yes, and it has effectively a sensor inside the tracking head, which can see where the ball is and can steer the laser beam to follow the ball at all times.
Just in front of us, there's a metal block, and so if you wanted to accurately measure the height of this, you would just place this reflective ball at the bottom of it, then at the top of it, and then you would know what that distance is.
That's right. At each of those 2 points, I would measure the coordinates of the ball, and then from the coordinates of those 2 points, I can work out the height.
So how is it applied to the aviation industry?
Aircraft require some very tight tolerance manufacturing. What you'll see people in the aircraft industry using laser trackers for example, would be for measuring the alignment of hinge units on the trailing edge of aircraft wings. For example, hinge units for the flaps. You might find people crawling all over the wing surface measuring the aerodynamic profile, because that can be quite important, especially close to the aircraft body.
That's quite an interesting image, just seeing someone all over a wing holding this very small ball for accurate measurement.
It's bizarre when you sit and watch somebody doing it, because they appear to be cleaning the wing, whereas in fact they're making very precise measurements.
And what other industries could it be used in, or what are other applications, say, of this method?
Space industry use them, for example, for aligning components on satellites. It's very critical to get the mass distribution correct, to align thrusters through the centre of mass of the spacecraft, so that when they fire, it doesn't spin off into infinity. So any area where you're making big things that require very high accuracy.
That was Ben Hughes, and before that, Jonathan Williams, both from the National Physical Laboratory and speaking to our own Meera Senthilingam.
You're listening to The Naked Scientists with me, Kat Arney, and with Ben Valsler. Still to come, Dave builds his own laser in kitchen science, world domination on the way, and we find out how fast the light from your headlights will go if you're driving near light speed.
Now, one of the many new applications of lasers is in the building of tiny, tiny machines. A small device that builds a smaller device and so on down to atomic level was a dream of Nobel Prize Prize-winning physicist Richard Feynman, and he inspired many researchers to try and find a way. Now, when handling tiny objects, you need tiny tools, and lasers make very good tweezers. Now, to find out how they work, I went to Bristol University and met physicist Dr. David Carberry.
The goal of our research was to follow Feynman's dream. So this is where you've got a large machine that makes a smaller machine, that makes a smaller machine, until eventually you can control individual atoms. We're not quite near that stage yet, but we're at the stage where we can definitely build a microscopic machine. We're currently using a large machine that uses a focused laser beam to manipulate small particles around.
So in order to realise your dream, you need to be able to manipulate things on a tiny, tiny scale. And you are actually using light beams as if they were tweezers.
That's absolutely correct.
Surely tweezers have to be something somewhat more solid than light.
It really is a focused beam of light. Imagine you've got a glass sphere sitting in front of you. If you shine a laser beam through that, it will bend towards the centre. This means there has been a change in momentum, which has to have been transferred to the glass sphere. In the case of a glass sphere that you can hold in your hand, the amount of momentum transfer you can't detect. But in the case of something very small, around the size of a red blood cell, then this has a very large, profound effect. It moves into the focus of the laser beam, and this is an optical trap, or an optical tweezer.
So the system you have, the holographic optical tweezers, how do they work? Where do you start with that?
The simplest way is you have a laser beam that is passed straight into a microscope. If it goes through a very high objective lens, so a very high numerical aperture, very high magnification, then you form an optical trap if the laser is strong enough. You typically need around 50 milliwatts for the base optical trap. To give an indication of how strong the magnification needs to be, we've got a 100 times objective lens, which focuses a 5mm laser beam at a distance of about 100 microns, or the thickness of one hair. It's very tightly focused, but this is absolutely required to form a sharp enough laser gradient to hold a particle at the laser focus.
So you can very tightly focus a laser, which means that you can hold something in what you call an optical trap. But in order to construct things, surely you need to bring more than one thing together, so you'd need more than one laser.
That's right, but we don't strictly need more than one laser. If we use a hologram, we can break one laser beam up into several outgoing parts, and then we can control the pattern of the light that comes off that. So as the laser reflects, it interferes with itself, just like you'll see at the beach, the waves will interfere with each other. And this we can then use to reconstruct several laser beams in the focus of our objective.
Well, that sounds really incredible, but also very complicated. How on earth do you actually control it? How do you do the physical work of bringing two things together?
We've got a number of methods. The first one is the simple one. You've got a couple of points on the screen with a mouse, and you click on the optical trap you want, and you move it closer to another optical trap. There's another one where we've got special gloves that you can put on. You can move your fingers closer together, and you can move these around the screen, and you can move the particles closer together. But our most recent thing, we've got a touch screen that we can touch with multiple fingers. Wherever we put our fingers, we form an optical trap, and we can manipulate this in real time, and we can start assembling, we can start whatever we choose to do.
Could I have a go? It sounds like something that you don't need much training for.
I can teach you all you need to know within 30 seconds using this multi-touch. Let's give it a shot.
At this point, David showed me into the laser room. The holographic assembler itself is housed in a large box, as the lasers are powerful enough to cause permanent eye damage. On the top of the box is a microscope with a camera focused on the tiny glass beads that the laser can move. The feed from this camera is then fed through to a computer where you can interact with the beads in real time.
This is our multi-touch table where, if you stick your finger on it, you will be able to manipulate the glass spheres that are sitting on the screen.
So does that mean that while I'm pressing on here and moving my finger around, I'm actually dragging around a tiny glass sphere over there on the microscope?
That's exactly correct.
And how big are these?
These are about 2 microns, so about a third the size of a red blood cell. But let's put this into perspective. One of these is 50 times smaller than the width of a human hair.
So these really are tiny. What's the next stage? What do you hope to develop next?
The next stage is to develop a few more applications. We're currently looking at 2 different projects. We're trying to make some nanotools. If we use a nanorod with 2 of these glass spheres, we can stick it together and form a kind of pointy stick that we can poke very hard into another object. So we could start feeling the forces on a cell as we poke it.
And that would be able to tell us things like how strong the membrane of a cell is. And I assume this is something that we've just never really been able to measure before.
We have been able to measure using the atomic force microscope, but that assumes that it's sitting on the surface, and this isn't always the case. Sometimes you've got cells that are floating around in solution, and you want to be able to test these in the natural environment, so you don't want to stick them down.
Let's see the videos of some of the things you have been able to build. What's this? It's very pretty, and it seems to be a series of connected rings, almost like the Olympic logo over and over again.
That's right, but instead of being just rings, these are actually these glass spheres we've just been manipulating on the screen. And in nature, if you start assembling these, or you leave it to gravity, they will form this sort of close-packed structure. And you've probably all seen this with a pile of beer cans. You stack them all up, and they all fit into each other's cavities. Now, it's the same with all bowls. You can stack them the same sort of way. But what I've got on screen is I've deliberately omitted a particular line of these. So if you've got your stack of cans, we've now deliberately taken out one particular line, and if we shine a laser beam through here with different frequencies, some laser light will get reflected, some will transmit through, and some will go round the corner. And this is a photonic crystal.
So because we have a gap in the middle of this collection of glass beads, you get some very particular interactions with light. What's this useful for?
In the past, we had something very similar with electronics, and we ended up forming the transistor. Now, this has gone on to revolutionise the electronics industry. We're hoping that a photonic switch like this will go on and revolutionise the next generation of device.
Dr. David Carberry from Bristol University on how optical tweezers can be used to build transistors for light and nanotools to study cells.
But not for plucking your eyebrows. Now it's time for this week's Kitchen Science, and it seems Dave Ansell has unveiled his plans for world domination.
This week I've had a go at building a laser, which has given me an awful lot of respect for the guys who built the first one 50 years ago.
Now, building a laser sounds quite a long way from our usual kitchen science type experiments. This, I'm guessing, is not something you recommend people try at home.
The design of this laser is actually very simple. It was developed by Scientific American in the 1970s, but it does involve a couple of pieces of kit you wouldn't find lying around the house, and it is very dangerous, so don't try this at home.
We will, of course, put pictures and video of the setup on the website at thenakedscientist.com/kitchen science. What do we actually have here?
The basic part of this laser is two pieces of metal aligned edge together with about 1.5 millimetres between them. And that gap is filled with basically normal air. And there's a few capacitors and a high voltage power supply and a spark gap, which is designed to apply a very, very large voltage, about 10,000 volts, across those two pieces of metal very, very quickly in a few nanoseconds.
How does air with a voltage through it equate to a laser?
It's the nitrogen in the air which is being active in this case. When we apply very high voltage to that nitrogen, we give the atoms of the nitrogen lots of energy. It just so happens that nitrogen is arranged in such a way as you can apply lots of energy to it, and you can end up with two states which an electron in that atom can be in, and you get more of them in the top state than the bottom state.
So when we apply our voltage, electrons on each molecule of nitrogen that's in that gap jump up to a higher level. So the nitrogen in there is excited. And how does the excited nitrogen then lead to giving us the light that we think of as a laser?
There's a couple of ways in which an atom can lose that energy in the form of light. One of them is by spontaneous emission. That's when an electron in the atom drops down a level, it emits that energy as a photon of light, and it goes off in random directions.
And that's the sort of thing we see in a conventional light bulb.
That's right. Now, there's a second way that the atom can release the energy, and that's if it's hit by a photon of exactly the same frequency as it would be trying to emit. This stimulates the emission of a second photon, which is in exactly the same direction as the first one.
So because we've got so many of the same element in there, in this case lots and lots of nitrogen, the energy gaps are going to be the same. So every photon that gets emitted has quite a high chance of hitting another of the same element, which means it has the right energy levels to get that element to release another photon. Those two photons can cause another two photons each to be released, and we get an exponential build-up of light coming from this excited nitrogen.
Yes, as long as we've got more atoms in the excited state than in the not excited state, because if a photon hits a not excited atom, it will get absorbed and it will stop. And this is the reason why we've got to do everything so quickly with this laser, because that excited state only lasts a few nanoseconds. If you wait too long, then it won't work anymore.
I can see how the excited nitrogen means that we could get much more light out, but still that just sounds like light to me and not a laser.
Well, if you started off with only one photon, as you would do in an ideal laser, then all the other photons are essentially copies of that first photon. So they're all going in exactly the same direction. They're all moving in the same phase, which means as a wave, they're all beating in time. And this is what laser light is. Laser just means light amplified by stimulated emission.
That's how it actually works, and that's the principle behind it. Let's switch it on and have a go. Now, do I need to back away or wear any protective equipment?
Definitely don't touch the metal bits because they're high voltage and very dangerous. I'm going to turn on a vacuum pump to start off with because I've reduced the pressure in there. Everything lasts for a bit longer and it works a bit better. It should work without it, but I haven't managed to get it to. So yes, stand back, don't touch anything. So when I press this button, that will charge up the capacitors. When they're charged enough, they'll discharge very quickly, applying that very high voltage.
And how are we going to see the laser?
Well, the laser ought to be in the ultraviolet, so invisible, but just a normal piece of white paper should glow when it gets hit by ultraviolet light.
Let's get it fired up and see what happens. So every one of those clicks is actually a spark happening, and looking at the bit of paper, I can see that it doesn't light up every time, but every now and then, on every fourth or fifth click, there's a bright flash on the paper. It looks really bright blue. Is that laser light, or is that just the light that we're seeing from that spark?
What you're seeing isn't laser light, but I think it is laser light which has hit this piece of paper, and then it's glowing, and you see the glow from the paper.
So we're seeing the effect of the laser, if not the laser itself. But again, the spark is very bright. Could we not just be seeing the spark shining through onto the paper?
For it to be such a nice tight spot, the only way you get that good a focus would be if the spark was a long way away, the other end of the channel between these two bits of metal. And in that case, it wouldn't be that bright.
So because the spark is quite a long way from the paper and it also gives out light in every direction, we wouldn't see a focused spot on the paper. We'd see a dull glow, if anything. And the spot itself is evidence that you have actually successfully built a laser in your garage.
Eventually, yes, and I think it could be a lot better, but it's just about a laser.
Now, this laser, as we could hear from all the clicking and see from the sparks, goes off for a very, very brief time every now and then. But a lot of the lasers that I've seen before, even simple things like laser pointers that you use in lectures, they're lit all the time.
Laser pointers are by no means simple, but they are quite common. Basically, if you can get a state which lasts a lot longer, so you can use other gases, things like helium and neon, or you can create a similar state in a semiconductor like in a laser pointer, you don't have this nanosecond period where it'll work. You can actually keep pumping energy into that high energy state, and it will keep on lasing until it runs out of energy.
So by using something like a semiconductor in the laser pointers, it's the equivalent of the nitrogen atoms in your laser being constantly excited and not dropping back down to the lower level.
That's right. It's basically a much better designed thing which you're trying to make laser.
So having successfully built a laser, what's the next step in your world domination, Dave?
I think going inside and having a cup of tea.
And that's all for Kitchen Science. This week we'll be back with another experiment very soon.
So not quite Dave's evil plan. There's pictures of his homemade nitrogen pulse laser online at thenakedscientist.com/kitchen science, plus loads more experiments you can try at home.
Distilling the best science. The Naked Scientists.
Today on The Naked Scientist, we're talking about lasers, and we've still got Graham on the line. We've got a question for you from Paul Anderson. Could a laser be used to fade and remove graffiti?
Yes, it can. They're already used in this application, I think, certainly for cleaning expensive things. The trick is to choose a laser so that the colour of the laser light matches the colour of the graffiti ink. So, it's a very neat solution for cleaning dirty stuff off expensive things. Unfortunately, it's not always cheap, and you do have to make sure there's no one around.
Is it also true that you can use lasers to have a look through the paint and try and find fraud in paintings?
Yes, you can. Again, you choose the right colour. Now what you're looking to do is to choose a colour which is not absorbed by the top layer of paint, so it goes straight through. It'll be absorbed by something a bit lower down, it'll bounce back off that, and whether it's there or not, you will get bounce back or not, and by mapping out the bounce back, you can look at the layer below the paint layer.
We've also had a question from Dom in Newmarket that came in on the phone. He wants to know if lasers give off extreme heat, and if you come into contact with them, can they be harmful?
Well, some do. It's not just true of laser light, in fact. You'll know that if you've got one of those really, really powerful torches, you're warned not to put your hand directly in front of it. It will also be giving off a lot of heat. And that really reflects the fact that heat heat at least in the form of thermal radiation, and light are just the same sort of stuff. If you like, light goes blue, green, yellow, orange, red, infrared, heat. And you can get lasers that work in the heat part of the spectrum as well. Some of them are very long wavelength indeed. Cutting and welding lasers, for instance, will put out 10,000 watts of heat at the most powerful end.
10,000 watts seems an awful lot.
It is if it's focused to a small spot and your finger's in the way.
Talking of a small spot, Oilinki on Twitter says, with the best laser, how small a spot could you focus from Earth to the moon?
Oh, goodness. Online mathematics, tricky one. You're trying to find a thing called diffraction, and that depends on how big you can make your laser beam down at the Earth. Back of the envelope calculation spreads out about a wavelength in 10 metres, so it's 400,000 kilometres to the moon. You'd probably get something about 40 metres across. And back to your football metaphor from earlier, we'd be looking at something about twice the size of the 18-yard box.
Excellent. So football on the moon by laser light. Anyway, now it's time for our question of the week with Diana O'Carroll.
This week, how illuminating can lights be at light speed?
Hi, my name's Larry Knight, and my question is, what would happen if you were driving at light speed and you switched your headlights on? What about a lit torch being carried at light speed? What would happen then?
But in physics lessons we're told that the speed of light is constant in a vacuum, so can shining it whilst moving extra fast make any difference?
I'm Dominic Ford from the Department of Physics at Cambridge. You probably had the experience at some point that a fire engine's driven past you, and as the fire engine's been driving towards you, you've heard it sound high-pitched. And as it's driven away from you, you've heard it sound low-pitched. And that happens because sound is a wave, and the Doppler effect says that the frequency is changed when you're moving relative to the source of the sound. Now, light is also a wave, and so it also shows the Doppler effect. But you have to be travelling very much faster before you see any effect. So if you were driving your car at close to the speed of light, an external observer would see that your front headlight would appear more blue than normal, and your rear tail light would appear more red than normal. The driver himself wouldn't actually see anything different from normal because he's not moving relative to the source of the light, just as the driver of a fire engine hears his siren at a constant pitch because he's not moving relative to the siren. Looking out of the window, though, the driver would be moving relative to any landscape that he was moving past, and he would see objects in front of him appear bluer than normal, and objects behind him appearing redder than normal. Of course, if things move very much faster, for example, a plane moving at close to the speed of sound, you get a sonic boom. And you get a similar effect with light. But unfortunately, Einstein's theory of special relativity says that you need infinite energy to make something move at the speed of light, and so you can never actually get there and observe that effect. There is one exception, which is when a relativistic particle travels in a material like glass, in which light travels at slightly less than the speed of light. Sounds ironic, but it's true. When the particle produces some radiation called Cherenkov radiation, which appears as a flash rather like the visual equivalent of a sonic boom.
To the driver, if he or she had infinite energy and hadn't imploded by then, the lights would look perfectly normal. To an observer, there would be a colour shift with bluer headlights and red tail lights becoming, well, more red, if that's possible. And objects which do move faster than the speed of light will produce this Cherenkov effect, the sonic boom of the light world, and you can see it as a blue glow in some nuclear reactor chambers. On our forum, Diver John was right in there with the Doppler shift analogy, and JP also threw in the red-blue changes. JP also added some links to computer simulations which can show you what you might see when travelling like a relativistic particle, and you can find those at thenakedscientists.com/forum in the QOTW thread. Next week, what would you see if you were a dog?
Hi, I'm Tom from Wales, and I'd like to know why dogs can't watch old-style CRT TVs And can they watch newer TVs like plasmas or LCDs?
Does your dog like detective dramas, current affairs or comedy? Let us know what you think the answer is by emailing chris@thenakedscientists.com or by writing on the forum, and the address is thenakedscientists.com/forum.
Thank you very much, Diana. That was Diana O'Carroll with our question of the week. You can find that online at thenakedscientist.com/QOTW or as its own podcast by searching for Question of the Week on iTunes. Now, sadly, that's all we have for this week. Many thanks to Kelvin Kem, Robinson Fulweiler, Graham Hurst answering all of your laser questions, and David Carberry for joining us this week. And to our production team, Mira Senthilingam, Dave Ansell, Tom Simpkins and Sarah Castor-Perry. Next week, we are celebrating some seriously small structures. We'll be finding out how nanostructures could help us safely store and access hydrogen, as well as looking at the nanostructures that form in batteries, both good ones and the bad ones. Get your questions into chris@thenakedscientists.com, and we'll be back with you next week.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.